This tutorial is about advection equation in 1D and its implementation using numerical methods. So if we look at the overall Burger's equation, we have the advection term and the diffusion term and the source term. And one way to do is just use the advection terms, and over the course of time we will add the other terms. But in this tutorial we will look at the advection term only. So the problem given to us is that we have a 10-meter long of open channel reach, and the water is flowing at 1 meters per second. And somewhere upstream we place a small pollutant, and we are assuming that there is no diffusion, so there's pure advection going on. How is this pollutant going to behave over time? And if we remove all the diffusion terms and we convert the Burger's equation into 1D, we have the time derivative of the concentration is equal to the minus times the velocity times the spatial derivative plus the source term. And of course, in our case, source term only applies initially at 0, 0 time, and then there is no source term. So we have only one small piece of pollutant, and we want to see how it behaves over time. And here is the discretization of the equation, and this will apply pretty much to all cases with some more terms or less terms. That on left side we have the time derivative, and on the right side we have the space derivative. And what we do is we apply basically the Euler's equation. If you remember the Euler's equation, that the time derivative is some slope function, and what we are trying to do is find c knowing this slope in time. So Cn plus 1 will be equal to Cn plus delta t times that slope, the slope, which in this case is, it's missing a minus sign here, so it will be minus u times Cin minus Ci minus 1n divided by delta x. So here I have corrected it. So there's a minus velocity term, and in this case we will assume the velocity to be constant, but keep in mind that the velocity itself could be changing with time as well. So it could be a function of n, and it could be changing in space as well. And then we have the source term. So we will implement this equation in MATLAB. And before we begin, I will give you a general template of typical implementation of these kind of problems. So first of all, we will have the equation, then we will provide the domain, which includes space and time. Then we'll define some variables, including field arrays, which are variables as well as the parameters. Then we will also set up some initial condition for these variables, and then we'll step through time. And as we are stepping through time, we will update the boundary conditions, we'll update the source information, find the solution implementing the discrete equation, check for any convergence values or error values that we may want to track, and then we can visualize at some selected steps. We may not want to visualize at every step because things might be too slow in that case. But within this step, we always clear the screen or the figure, we put some display commands, we show graphics, and then we pause for a little bit to view the figure. Okay, so now we're going to implement the advection equation. So let's save as, and we'll save it as convection 1D or advection 1D. Advection 1D. Okay. And we know that our equation is Ct is equal to minus u times Cx, and I'm not going to put the source term here because we will see that source only appears once in the whole equation, or maybe we can, plus some Qc, which is the source. Okay. So our space is Lx is 10, which is the length of the domain, and let's run it at dx is equal to 0.5. So every 5 meters, every half meter. So this gives us the number of nodes and I always think we should use fix command. This basically converts it into an integer, because we can only have integer nodes. And so this gives us the number of nodes, and at the same time we can define our line space for plotting purposes. So 0 to Lx with nx nodes. Similarly, we want to set up the time part. So let's say we want to run it for 15 seconds, and we want to find what dt is. As I have said before, that this depends upon the CFL condition. So let's say CFL is equal to 1 in this case, and I will explain why I've picked 1 in this case. So then dt is CFL times dx divided by the velocity, and in our case we are setting the velocity to be 1, which we already know. So after we have this information, we know how many time steps we need, which will be again fix t divided by dt. So this is the number of time steps that we will need to run to complete our simulation. Now we get to the variables part. So c is all zeros of nx time 1. So these are the nx locations where we want to compute c. And our parameter is the speed, which is again zeros, nx, and 1. And our initial condition is whatever is happening at t is equal to 0, and we know that all the concentration are 0, and all the velocities are 1, which we have given in the problem. So now we go ahead and start the simulation here. I will skip the boundary conditions at this point, but provide the source. So if n is equal to 1, which is the first step, what we want to do is we want the first value of the concentration to be equal to 1. Although in the problem it's given q, let's just set it to 1 for now, but you can set it up to whatever the value of source is. And then we start our solution where we say t is equal to t plus dt. So I'm finding the next step, and so to do that I need to save my current value. So Cn, which is the current value, is equal to C, and so those two steps definitely have to be done. And after that I can start my loop for I equal to 2 to the end of the spatial domain. I'm going to update at each point the value of the concentration. So C I is equal to C I, so the previous value, which is Cn I, plus dt times something. Okay, so this is my Euler's method, if you remember. And so what is that something? Well, that something is coming from my advection term, which is A. Let's call this A. And so this will be A. Let's go back and look at this part. So this is the new value of concentration is the old plus delta t times this term, which is the advection term A. So now we will also put advection term here, which is nothing but minus the velocity at this location times the spatial derivative, which is the current value at this point minus current value at the previous or the left node divided by dx. So I hope I'm not making any typos here, but this will do the job. So this is advection term and then the update term. And source we have already added here, so we don't need to include source here. And then at this point I'm going to skip the convergence, but let's plot these values. So first of all, we plot the x versus time concentration with maybe a circle and line, and then we put a title on top of this, which is sprintf. So typically it's a good idea to put the time value to f, which is 2 decimal places, and the value of time. And we also want to set up the axis at this point. So our x-axis goes from 0 to Lx, and then the y-axis, because my source is 1, I'll probably go from 0 to 2 on the y-axis, and then show and plot. So this looks like it. So usually when you run it for the first time, you might see some typos or some typos in the code, or even there could be some syntactic errors. But in either case, let's run it. And it looks like it's running, but I'm not. The value is not going back to 0. So let's go back here and see what happened. So if you look at this source part, at n is equal to 1, I set up c1 is equal to 1. But then I never update that information. If you look at this, it's always changing values from 2 to nx, but c1 always stays 1. So in order to fix that, we have to make sure that we let it know that otherwise c1 is equal to 0. So it's not treated as a source for all the times. And so when n is equal to 1, set the value of the first node to 1, otherwise keep it at 0. So now if we run it, you can see how you see the progression. And now let's make it a little bit slower so you can see at each point. So so as you can see, this is pure advection. There is no diffusion going on. The height of the concentration stays same through the simulation. Now something at this point would be good to talk about is the periodic boundary. So just like when we look at the surface of the Earth, if this was the convection going, say, along the equator, when it reaches this point, it has actually gone back to this point, because Earth is a sphere, so there's a connectivity of this point back to this point, and that's called a periodic boundary. We need to take this back over here. So in order to do that, let's add just one line here, that C1, which is the value of the first node, is equal to C end. So whatever is at the last point goes back to the first point. Now you will see when we now simulate it, it will reach here and it should re-enter from the other side. And again, I think now we have to remove this part, because we are continuously saying that set it equal to 0. So in case of periodic boundary, we don't really need this part. And now you can see how this will just go across and keep moving across every time. So this is how you can program the advection equation. Now I wanted to go through this. This is a little bit longer tutorial because I wanted to show you the overall general format, and this is what we will be using for all the other implementations.